The race to Mars just changed. Forget everything you know about how we build rockets, because NASA is doing something radically different. They're not just launching engines anymore, they're assembling them in space. The MARVL project could slash the time it takes to reach Mars and completely change how spacecraft are built. Why nuclear electric matters. If humanity is serious about going to Mars, our propulsion systems need a revolution, and nuclear electric propulsion, NEP, could be that leap forward. Unlike traditional chemical rockets, which burn propellant in a powerful but short-lived burst, NEP systems offer a slower, more consistent, and vastly more efficient alternative. Powered by a compact nuclear reactor, these engines generate electricity that charges and accelerates particles like xenon gas to produce a gentle but continuous thrust. While that may sound underwhelming compared to the roar of a Falcon 9 launch, this slow burn adds up. A spacecraft using NEP can accelerate for months, gradually building up incredible speeds that make deep space travel more realistic. This method could shrink a round-trip Mars mission from 3 years to just 2 years, dramatically reducing the time astronauts would spend exposed to radiation and isolation. The efficiency comes from a much higher specific impulse, a measure of how much thrust is produced per unit of fuel. Chemical rockets typically hit around 450 seconds of specific impulse. NEP engines? They can reach over 10,000 seconds. That's an enormous leap in fuel economy and performance. Inside MARVL's radical design. NASA's MARVL project, Modular Assembled Radiators for Nuclear Electric Propulsion Vehicles, isn't just a technical upgrade. It's a total rethinking of how we build spacecraft for deep space. One of NEP's biggest challenges is managing heat. When a reactor is continuously generating electricity, it also produces large amounts of waste heat. In space, there's no atmosphere to dissipate it, so radiators are the only option. But these aren't ordinary radiators, they're massive, and they need to be deployed flawlessly to prevent the system from overheating. Here's the problem. Traditional spacecraft design assumes that everything must fit inside a single rocket fairing. That's the cone-shaped tip of a rocket that protects the payload during launch. But NEP's heat radiator array, when fully deployed, would be roughly the size of a football field. There's simply no way to fold something that large into a single launch vehicle. That's why MARVL is so bold. Instead of cramming the entire radiator into one rocket, NASA proposes to launch the radiator in modular parts. Panels that can be autonomously assembled in space by robots. Once connected, these panels will circulate a liquid metal coolant, such as a sodium-potassium alloy, NaK, through the system to carry heat away from the reactor core and radiate it into space. What this unlocks. The implications of MARVL extend far beyond solving one technical bottleneck. They redefine what's possible in human spaceflight. Once this modular, robot-assembled NEP system becomes operational, it changes how we plan and execute every aspect of Mars exploration. And more importantly, it opens doors to missions we haven't even dared to consider yet. First, let's talk about crewed Mars missions. The current timelines are long and risky. A 3-year round trip exposes astronauts to months of radiation, muscle atrophy, and psychological strain. NEP systems like the one MARVL supports could cut the round trip to around 2 years, making missions safer and more logistically feasible. With that, Mars shifts from being a high-stakes gamble to a manageable expedition. But MARVL's ripple effect extends beyond crew transport. It enables modular cargo systems, spacecraft that ferry supplies, habitats, and return vehicles ahead of the crew. It also aligns perfectly with NASA's Artemis program, which envisions a sustainable presence around the moon. Even more compelling is the role this tech plays in deep space science missions. Imagine telescopes parked in stable Lagrange points, powered for decades. Or robotic missions to the icy moons of Jupiter and Saturn, carrying scientific payloads heavier than anything we've launched before. Nuclear electric propulsion enables that kind of endurance and payload mass, and MARVL makes it scalable. Building the future in orbit. NASA's MARVL project isn't just about solving a heat problem. It's a bold declaration that the era of cramming spacecraft into rockets is over. For the first time, we're building critical propulsion infrastructure in space, using robots, precision engineering, and nuclear power. That shifts the entire foundation of how we explore the solar system. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching, and see you next time.